everybody. It's almost 10 past 3. We are here now today with jaseg, who's going to talk us through tamper-sensing in the wild, which is about tamper-proofing things electronically, tamper evidence and tamper-sensing, and we've all had contact with this with our lives every time we get a letter from our bank, for example, with a PIN number. That's, for example, tamper-evident. If someone's opened it, you can see the number's been read, but not destroyed. And this is something that's going to happen with the electronic devices that jaseg is going to tell us about now. Just a couple of things about them. They are currently doing their PhD. They're finishing it in hardware security. They held a few other talks as well at GPN and other chaos events. But without further ado, I wish you all the best and a warm welcome for jaseg.
Thank you. All right, let's get started. So I'm going to talk about tamper-sensing meshes. What is a tamper-sensing mesh? A tamper-sensing mesh, even though the name suggests something woven, it's usually actually a looped conductor. Usually today in like sort of a circuit board, a flexible circuit board, something like that. That is meant to detect attempts at physical intrusion into a device. The type of attack it detects is like drilling, sawing, anything that would like penetrate this like foil or board covered in this looped conductor that would break the conductor. Usually it's implemented in a way that it triggers some tamper response at the immediate instant that it gets broken. That oftentimes is deleting keys, raising alarms. If any of you have ever taken apart a payment terminal, like they kind of do that kind of thing. They start beeping or they like show warning messages when you like try to open them up. Can also be other stuff like explosions maybe. Contact me if you want to do some research. They're widely used in devices like hardware security modules, payment terminals, ATMs, nuclear weapons, many applications for this technology. The history goes back a surprising amount of time. The first references I could find were from the 1870s, where people were using basically that to cover walls of bank vaults in order to protect them against attackers wielding pickaxes, breaking holes into the vault. There is like later references where like when they started to get like multi-layer constructions, when printed circuit technology was applied to them, and they found like widespread commercial adoption in their modern form in the 1990s. There is some examples from, or some references to their use in like Secret Service and military applications, but they're very hard to date because they're like usually not very explicit in like how they're used and when they started being used. Their commercial applications today are things like data center HSMs that are used for like key management, payment processing, certificate infrastructure, also card payment terminals where they're used to encrypt pins because the pin pad needs to be physically protected. ATMs, I mentioned, they're using them, but like it's not the entire ATM that is protected, it's specific components such as the ATM pin pad. If any of you have ever taken one apart, they're like their own little cryptographically secured hardware protected package so that the pin is encrypted right when it is entered into the device. They're also used in Germany in certain designs for key safes for public buildings so that the fire department can get a hold of a master key quickly. They use those as a protection against somebody drilling into the thing and like stealing the master key. They're also used in certain mail franking machines that are machines that were used back in the day to like print postage stamps on an envelope without like physically handling stamps. And they're also used in certain types of slot machines, at least around here in Germany, where they're used for like the CPU module inside of the slot machine. As far as I know, this is not for any regulatory purpose. As far as I know, it's just for DRM. We did a survey where we went on eBay and we bought random electronic waste to take apart. We found 23 different card payment terminals, 3 ATM pin pads, 2 data center style HSMs, 1 franking machine, and 1 of these slot machine CPU modules. First, the conclusions that we found. So how do they actually build these meshes? Surprisingly, it's all pretty run-of-the-mill stuff any of you could order on like whatever PCBWay JLC PCB. There's like rigid PCBs with like completely reasonable design rules. Smallest we found was like about 100 micron tray space. There's polyimide, like regular brown polyimide copper FPCs. There's like some silver and carbon ink FPCs with these like usual structure sizes for screen printing processes, so really coarse. There's some laser direct structuring, LPKF tech, if any of you know it. Unfortunately, that company kind of stopped making these machines, so that's kind of a technology that's on its way out. And there's like this one particular example we found of like a IBM Gore style mesh, funnily enough used in a Ultimaco HSM. So yeah, make of that what you will, which also uses a surprisingly coarse structure size. So takeaway is you can do it yourself. This is like external photos. This is all going to be uploaded later. And internal photos of what we took apart. You can zoom in the digital version of this talk if you're interested. So what layouts did we observe for these Tamper-Sensing meshes? First of all, here's like 4 examples. One thing they sometimes do is like they offset multiple layers so that you have less area between traces where you could stick something through. We have observed sort of orthogonal patterns where they even attempt to like lay out 2 layers in a way that they're like orthogonal to each other to make it harder to like slot something in between layers. We found like the example on the bottom left is like from IBM style mesh out of a Ultimaco HSM that uses like multiple layers with like different patterns in order to provide better area coverage. And the bottom right example is from an ATM pin pad where it used like multiple layers spaced apart, presumably to make it more difficult to like stick something through and then like pinpoint like some specific spot. The materials and manufacturing techniques we saw there is like, I mean, rigid PCBs is everywhere, like payment terminals commonly use those. Flexible PCBs also often used in payment terminals because they're cheap, but then also like silver ink and carbon ink processes, especially used in like payment terminals for like pin pads, protecting the pin pad. This is like all off-the-shelf processes. D shows like a close-up shot of like a laser direct structuring method where the mesh is like printed using a photo-activated chemical process on a plastic part in 3D, which is kind of cool, but it's like super rare. Like we found that in one particular Stripe terminal and not in others. And then like E is like a close-up of this IBM process. They use like a carbon ink process, but a custom one that is designed in a way that is like especially difficult to take it apart without breaking the traces. The connecting methods between the meshes and the rest of the device that we found is like basically everything you could imagine, right? You see soldered connections, you see B is like zebra strip connections. It's like the stuff you usually use to connect to LCDs. It's like a flexible conductive stuff. You see C where somebody repurposed a EMI gasket, which is actually meant for something entirely different to connect to a mesh. You see like FPC connectors for like these foil meshes being used. And then like E is just like any sort of like THT or SMD connector that you could solder. You can also use at least with the copper-based meshes where you can like solder a connector straight onto the mesh. F is a little bit funkier. That's something we saw like in some devices by Ingenico where they used like metal domes similar to the ones you use for like a foil keypad, but they use them as a contact, as a pressure-sensitive contact between the circuit board and the mesh. This also served as a like disassembly protection. Like if you disassemble the device, the contact would break. To print or to bring these meshes into 3 dimensions and protect 3-dimensional structures, we saw a bunch of things being used, like simplest one, A, you just fold it. Yeah, people did that apparently. B is like a little more interesting because like they folded it, but apparently they couldn't get it to overlap, so you have like a little gap at the corner, which is funny. C, laser direct structuring, is just an inherently 3D process, like you can pattern 3D parts with it, which is cool. D is a bit funky because there somebody thermoformed a mesh, so they printed the mesh and then they like embossed it into shape, which has some limitations, but it's like an interesting idea. And like E is the probably funniest one we found, where they like literally just hand soldered like multiple cards together. Like we call it House of Cards style construction. Yeah, here's another example of a thermoformed mesh out of an, I think, Ingenico payment terminal. The funny thing there is, like, after you remove the black cover layer, which I think is just meant to make it more difficult to see what's going on, you see that like they had some trouble apparently getting it reliably to work reliably after thermoforming. You can see that because the structure size of the mesh suddenly increases by like a factor of 3 when it gets into like the embossed part of it, where it like curves around, because clearly that was difficult to get right. Obviously, this has security implications. Yeah, make out of that what you will. We also saw some instances of like especially PCB meshes used in like a sandwich style, right? So like on A, you see like these small mesh coupons, you see them in payment terminals, must have some like standard reason why they're always in these devices and not others, where they like glue a little or like solder a little piece of PCB on top of another PCB that has like a tiny mesh embedded inside it. B shows one where like they did that, but instead of having the mesh in the planar direction, like you would expect it, it was like implemented with like a bunch of wires being interconnected, so like through holes in the PCB, doing like a vertical thing. C shows like multiple PCBs stacked to cover the backside of like a magstripe reader connector in a payment terminal. And funniest one was D, where they took one PCB, soldered components on top, and then above the components they soldered another PCB where they milled a cavity inside to like protect it from all sides without like actually having anything much more custom than a PCB with an extra milling step. Yeah, quite a cool construction if you ask me. We observed some security issues in our analysis. So like first of all, a lot of these meshes are like kind of incomplete. Like especially the payment terminal ones, they usually cover like 5 sides of the card slot, and the 6th side, well, you have to stick a card in, so you can't put a mesh there, which is quite funny. Also, meshes not overlapping at edges. This folding issue and leaving gaps where you could insert a probe is like really common, especially at corners. I think that's just like down to manufacturing constraints, because it would take like manual labor to do it in a overlapping way or something. And then like also gaps at the interface between a PCB and a mesh. Like a couple of years ago at a congress, like talk was presented by SR Labs, where I was like part of the research team where we did exactly that. We had like a payment terminal with like a really fancy laser direct structured 3D mesh, but you could just stick like a needle underneath the mesh and short circuit the readout circuit. Yeah, so like these gaps are an actual issue. The thermoform cavities that have like these enlarged structures is something we found multiple manufacturers had that issue apparently. So that's something to watch out for. And in one case, we had like this thermoformed mesh with this like very secure like cover lacquer, so you can't see what's going on, which you could just remove with like, I don't even know what it was. I think it was like isopropyl or acetone or something. You could just remove the lacquer without damaging the mesh, which is funny. Yeah, and also oftentimes, even when they put some sort of cover paint on top, oftentimes you are still able to see the traces underneath because it was like kind of printed and sort of 3D. So if you like positioned the light correctly, you could still see it, which is, I don't know, it's like kind of half-assed. Yeah. We can derive some design recommendations. So if you want to build your own security mesh, which I want to encourage you to do, there is a number of commodity PCB manufacturing design rules that you can just use as is. Yeah. So if you just use like PCBWay, JLC PCB, Eisler, whoever is like your fab of choice, just use the standard design rules, go to the lower end of them, and then you already have like a pretty decent security mesh with a better structure size than a lot what you see in industry. Avoid ink printing processes unless you have a really good reason to use one, simply because they're like, if they're silkscreen, they have like a really coarse resolution, and that just makes it much easier to attack, because if a tray space is like 500 micron, you can get like a almost 1 millimeter drill through that without actually breaking a trace if you're careful. So yeah, I don't really see a reason to use them in most cases. Yeah, think about your corner cases, literally. Yeah, because that's like where I see most of these designs kind of, I don't know, not really like, not really achieve their goals, and try to overlap meshes where possible. Use potting and cover layers, like they actually do work to make it more difficult to look at stuff, but like actually check that they work. Like if you have a cover layer, like a cover lacquer that is black, well, check that you actually can't see what's underneath, because otherwise it's a bit pointless. Yeah, and also check the chemical resistance, because a cover lacquer that you can just like scrub off with like isopropyl alcohol isn't really good for much. Yeah. More generally, try to mix tough potting or enclosure materials and fragile mesh materials, because that makes life much harder for an attacker. One device had like a super box standard silver ink printed silk-screened mesh, but that was potted in an epoxy, and it just happened to be that this epoxy stuck really well to the ink, and the ink didn't stick that well to the mesh foil. And even though it was like a completely standard mesh file process, like the same process is used for these really shitty computer keyboards, right? The like membranes inside them are made in the same process. It just worked super well because you couldn't peel it off without breaking all the traces. Yeah. If you can, consider using steel instead of plastic. It also makes it more difficult to take stuff apart without applying a lot of violence. And also, funnily enough, helps against X-ray inspection because steel absorbs X-rays. Yeah. Use thin substrates and thin conductive layers for the mesh, simply to make them more fragile, yeah, especially if you use copper. And yeah, try to balance the adhesion of the like conductor to the foil and the conductor to the potting material so that it's like difficult to take apart without breaking stuff. Try to overlap multiple layers of the mesh at a 50% offset, so you have like no gaps left in between if you like look at it against the light. It's not possible like always, like you always have like some little spots, but like it's an easy thing to do, and like I don't see a reason why not to do it. And if you can, try to space multiple layers of meshes apart in the Z dimension, right? So have like intentionally put some space in between, because that makes it more difficult for an attacker to like drill or probe through the mesh, simply because it constrains their freedom of movement. Yeah. And if you can, use a pressure-sensitive connection method to the mesh, something like tactile domes, because that also makes it much more difficult to take apart a device or to analyze the mesh if you have to take apart the device, and taking apart breaks the connection to the mesh. Yeah. This is something that's used in these payment terminals quite extensively, and which, even though it's like really dumb and simple, works really well, just annoying the hell out of you if you like try to like attack one of these devices. Yeah. So I thank you for listening. If you have questions, we have a little bit of time for questions. Now, if you could briefly blank the stream. Yes. This QR code leads you to a long form, like to my PhD thesis, which contains chapter 3, a long form written version of what I just talked about. Scan it if you want. It's going to be on screen for like a minute, and then I'm going to take it off again.
Okay, first of all, thank you. Warm round of applause. Thank you. So I'm just going to say that was really interesting. I didn't know a lot about it, and that was very interesting. Are there any questions? We have sort of 3.5 minutes. Yes, I'll come around.
Electrically, how is actually the how is it monitored?
Yeah.
So is it like, does it detect if like the mesh is bent and then the resistance changes or something?
Way less stupid. Like in most cases, what they do is they just apply like a pseudo-random bit pattern to make sure that the mesh traces aren't electrically completely broken, and to make sure there's no short circuits between the trace and ground or the adjacent traces. There's like this IBM Gore Utimaco example. They have like multiple segments of traces in the mesh that are equal length, made out of this carbon ink, which has a high resistance. And then they like have a bridge, like wired up as a Wheatstone bridge circuit basically, and have comparators check that like the resistance of these sections is like very close to each other. But that's the most advanced example that I found. Yeah.
Any other questions? Yeah. Hang on.
What is the most half-hearted attempt at protecting a device that you've observed?
Ooh, that's a very good question. I guess like we had one device, like a payment terminal, that just didn't have any mesh inside anywhere. I don't know. I think like I suspect it might have been like a terminal meant for like transport card use and not like payment use. It wasn't quite clear from the packaging. Yeah, but otherwise we had a couple where there was like a mesh inside of the PCB on an internal layer, but like at no other point in the device. So unless you like opened it up and like started drilling holes into it, it wouldn't have noticed, which is also kind of funny.
So there's time for one last question. I saw one here in the middle, or was that you?
This is very new to me. I'm still trying to wrap my head around how it works. So I was wondering, can't I just like bypass the area where I want to drill with like a cable with the same resistance?
You can theoretically do that. The thing is, these meshes are like always monitored. There's a backup battery and they're constantly being checked. And so you not only have to like figure out, okay, how do I need to wire this up correctly so I like bypass the part of it that I want to bypass, which is already quite difficult because you need to like reconstruct the layout for that. But also you need to like apply that bypass without triggering the alarm, right? So for example, a regular soldering iron would trigger the alarm because its tip is usually grounded, yeah? So it's probably possible. I would love to try it out, but I would say it's like about probably between like a bachelor's and a master's thesis in complexity.
Okay, I just have one quick question.
Yes.
Were you at some point worried when you ordered all these ATM keypads that the government was going to ask you about it?
To be honest, I don't think so, because it's surprisingly easy to find this stuff on eBay. The ATM pin pads, like some of these sellers seemed like a little bit sketchy, because except for one of them, all of them came from like private sellers, where it's like, why? But like for the payment terminals and other stuff, I found like some, I think, Lithuanian e-waste recycler, where they just sold them off in like lots of like 10 payment terminals for €5. It was great. I loved it.
Well, thank you for the answer. Thank you for your time. Thank you for the talk. And one last warm round for applause for jaseg. Thank you.